In this video, we're going to be talking about solving linear equations. And most of you have probably already done this at some point, but we're going to start off with the basics. We're going to start off with just solving single-step linear equations, and then towards the end of the video, we're going to review how to solve equations that are a little bit more complicated. So in this first section, though, 2.1, we're just going to deal with the one-step linear equations, and we're going to start out with some definitions. So the first definition is pretty basic. It's the definition of what an equation is. It's an equation is a mathematical statement that two expressions are equal. For example, some of the most basic equations are things like this: 2 equals 2. By common sense, we know that's true because the left-hand side is 2 and the right-hand side is 2, so they're equal. Second definition, we have now a specific kind of equation, a linear equation. A linear equation in one variable has a single variable, and the exponent on that one variable is 1. So a couple things to highlight again here is that there's one variable. So it has just a single variable, and the exponent on that variable is 1. So an example of a linear equation might be something like this: 2x plus 5 equals 7. This is a linear equation in one variable because, notice there's just one variable, x, and the exponent on that variable is 1. In other words, it's not something like 2x squared plus 5 equals 7. This is not linear. What about this one? 2x plus 5y equals 7. Is that a linear equation in one variable? Well, it turns out it is a linear equation, but it's not a linear equation in one variable. There are two variables. There's an x and a y. So this is a linear equation in two variables. In these couple sections, we're only going to be talking about solving linear equations in one variable, which is this type right here. So these are some that are not linear. So one of the first things we do when we start to talk about linear equations is solutions, and eventually we're going to be finding solutions to linear equations. But what if we want to know if a value, if x equals -4, is a solution to 6x plus 11 equals -13? Now remember, so a variable can be any value. We want to take x equal to a specific value, specifically equal to -4, and we want to check to see if -4 is a solution to this equation. Well, remember, for it to be an equation, the two sides, the two expressions, have to be equal, meaning the left side, the 6x plus 11, has to be equal to the -13. So let's go ahead and take that -4 there and evaluate the left-hand side of this equation if we plug that in there. Now, one of the things we want to get in the habit of doing whenever we're plugging values in is we always put them in parentheses. 6 parentheses -4. Very important that you do that. That in this particular problem, it specifies that this is multiplication and not 6 minus 4, but 6 times -4. And we have plus 11 equals -13. Simplifying here, we know with order of operations we multiply before we add. So we take a positive 6 times a -4, that's a -24, plus 11 equals -13. Now we can go ahead and add. negative 24 plus 11 is in fact negative 13. Now remember, it's an equation. If the two expressions are equal, well, these are equal. Negative 13 equals negative 13. So we can say here, we can say x equals negative 4 is a solution to the equation. Alright, so that's how we go ahead and check to see if values are solutions to equations. Now let's go ahead and start looking at how we actually solve one of these things. So before we do that though, we're going to take a look at a few properties. The first one here is the addition-subtraction property of equality. And it's pretty simple. It just says that if I have a statement that A is equal to B, and I add the same amount to both sides, if I add C to A and I add C to B, then look, there's still an equal sign between them. They should still be equal. In other words, if I have 5 equals 5 and I add 2 to both of those, I'll still have 5 plus 2 equals 5 plus 2, which equals 7. Let me write that out. If I have 5 equals 5, those are two things that are equal. Think of that as your A and your B. And I add the same thing to both sides. If I add 2 here and I add 2 here, it's still equal. It's 7 equals 7. And the same thing goes with subtraction. If I have two quantities that are equal, A equals B, and I now subtract C from both sides, guess what? They're still equal. Both sides are equal. And then the same thing goes with the other two main operations of multiplication and with division. So if I have A equals B and A times C equals B times C, that means that if A equals B and I multiply both sides by C, we're still equal. And then likewise, if I have A equal to B and I then divide both sides by C, they are still equal. Well, why is this important for solving equations? I like to think of that equal sign in an equation as the balance. This is the balance. And any of you that know anything about a balance, a balance is used to see if two quantities are the same. If two quantities are the same, this left-hand side will be at the same level as this right-hand side. But if I have just a little bit here and I have a whole lot over here, that's going to tip the balance this way, and vice versa. If there's more on the left side and less on the right side, it's going to tip the balance to the left. But if they weigh the same, if there's the same amount on both sides, if there's like 5 pounds here and 5 pounds here, that balance is going to be perfectly balanced and the two sides will be equal. But if I have 5 pounds on both sides, say that's 5 pounds there and 5 pounds there, and then I add in an extra 2 pounds there and I add in an extra 2 pounds there, are those two sides going to be equal? You bet it. You bet you they are. They're both going to be equal to 7. So that's the idea when solving equations. It's all right. You can change equations however you want. You can add things to both sides. You can subtract things. You can multiply, divide. The important thing is if you do it to one side, you have to do it to the other side. Let's write that down. Whatever you do to one side of an equation, you also have to do it to the other side. In order to keep the equation balanced. And the way we're going to do this is through the concept of inverse operations. The whole idea of concept of inverse is the word undo, or the opposite operation. For example, adding and subtracting are inverse operations. Can you think of any other operations that undo each other? We know if we add 2 and we take away 2, we get back to where we started. Also, multiplying and dividing. These are inverse operations. Okay? I'll talk more about what I mean by that in a second, but we're going to use this concept of inverse operations along with the idea of keeping an equation balanced to solve equations. So, just to sum it up, the goal when solving equations is to isolate the variable. Isolate the variable. What does isolate mean? Get x by itself. Plain and simple, that's what we have to do. We have to find out what that value of x is. We have to get it by itself. And again, a lot of you I think have done this before, but we're going to review it, assuming nobody, we don't want to leave anybody behind, so we're going to review even the most basic of solving equations. If this is easy for you, great. You're going to be ready for the more difficult stuff. So let's jump right in here. We have an equation. We have x plus 7 equals 12. Now ask yourself the question, is x by itself? Have we isolated x? No. We need to isolate. And the way we do that is with inverse operations. So notice this is x plus 7. The inverse operation of adding 7 is subtracting 7. Okay? Plus 7 and minus 7 are inverse operations. Now, remember, let's slide back up here. Remember, with equations, we need to keep it balanced. We need to keep it balanced, meaning whatever we do to one side, we have to do to the other side. So if I subtract 7 on the left, I need to subtract 7 on the right. Need to do it to both sides. So let's go ahead and subtract that. On the left side, plus 7 and minus 7 undo each other. They cancel each other out. So these guys will go away. Leaving on the left-hand side, all that's left is this x over here. So we have x over here equals what on the right side? Well, 12 minus 7, you should know that is equal to 5. Now let's go ahead and check. Remember, with an equation you can always check your solution. So we take our equation x plus 7 equals 12, and now we can go ahead and plug that in for x. When you plug it in, you get 5 plus 7 equals 12, and 5 plus 7 is 12, so that's good. My equation is x equals 5. Okay. Let's move on to example B. This is a similar sort of problem. Again, ask yourself, is that B by itself? No, we need to isolate it. Now this one's a little bit different because it looks like we are adding a number here. This looks like B is being added to negative 2.7, but when you add a negative, that's really, remember, like subtracting. I don't really care so much about this sign as much as I care about what's this number here. This overall number here is a negative, and the opposite of a negative is a positive. So to undo this negative 2.7, we actually need to add 2.7. But if I add it on the left side, I also have to add it on the right side. Okay. Again, this is good because over here, negative 2.7 and positive 2.7 are opposites. They undo each other, so those cancel. And what's left on the left side is just b. Now on the right-hand side, if I add that, I get 10.8. And again, we could check this. If I plug in negative 2.7 plus b equals 8.1, and I plug this 10.8 in for b, you get a negative 2.7 plus 10.8 equals 8.1. And it turns out when you add negative 2.7 plus 10.8, you do get 8.1. So we get 8.1 equals 8.1, which means 10.8 is our solution. Okay, hopefully this makes sense. Again, I think you have probably done this before, but we're reviewing anyway. We have a few more here in this section, not a whole lot more, but now we move on to the operation of multiplication. Again, ask yourself, is that x right there isolated? It's not. It's being multiplied by negative 4. So we do need to still isolate the x. We know this is multiplication here because no operation is written, so we can just assume that's multiply. Now if we go back to our inverse operations, let's go ahead and scroll back up here. Remember, multiply and divide are inverse operations. So since we have a multiply here, the opposite of that is divide. So let's go ahead and divide that. We're going to divide both sides by negative 4. Because remember, if we do it on the right side, we also have to do it on the left side. So negative 4 divided by negative 4, well, they don't really cancel. When you divide a number by itself, like for example 2 divided by 2, that equals 1. So this really is equal to 1 times x. Now, is it necessary to have the 1 there? Do we need to have a 1 times x? Well, not really. We can just, if we want, we can just get rid of that 1. We don't really need it in there. We can just leave it as x. But if you feel comfortable putting it in there, by all means you can do that. 20 now on the other side, 20 divided by 4 is 5, but since it's a positive divided by a negative, that's going to be a negative 5. Again, we can do our check here. We have 20 equals negative 4x. If we plug in negative 5 for x, remember put it in parentheses. So this is negative 4 times negative 5, and negative times a negative is in fact a positive 20. Those check out. Our answer is x equals negative 5. Okay, moving on, we have a fourth example. Again, we need to isolate this b. The b is not by itself. It is being divided by 6. Well, what operation is the opposite of 6? Of division by 6? Well, it's just like the opposite of the last example. We had 4 times x. Well, we divided by that negative 4. Here we're dividing by 6. We need to multiply by 6. So let's go ahead and do that. Let's multiply this side by 6, and then we have to multiply the other side by 6. Sometimes students like to write this because it's a fraction, like to multiply it by 6 over 1. That's not necessary, but if that helps you, you can. Now when I do that, notice what's going to happen here. The 6's will divide out, leaving what? What does it leave? It leaves a b, but that's not all it leaves. What else does it leave? That negative there. Now do we want to solve for b, or do we want to solve for negative b? Yeah, well, hopefully you said we want to solve for b. So we don't want this to be negative. Can you think of a way that we could change this operation we just did so that this becomes a positive b? Hopefully what you're thinking is instead of multiplying both sides by 6, we could multiply both sides by negative 6. We could multiply the right hand left side by a negative 6 instead of a positive 6, because when we do that, all of a sudden that becomes a positive b. And then our answer, 4 times negative 6, is negative 24. Go ahead and check. We have negative b over 6 equals 4, and b is negative 24, so this is a negative 24 over 6 equals 4. But a negative, the opposite of a negative is a positive, so this is 24 over 6, which is in fact 4. So that checks out. That's our answer. Okay. Hopefully this is all making sense to you. Again, if some of this you're still having trouble with, you can go into the math lab before class. We're going to do a bunch more of these in class though next time, so we can get help in class. The last one here is a bit more complicated because we have y, but then we have y times this fraction. And remember, the fraction bar in a fraction represents the operation of division. So what we really have here is we have y being multiplied by 3, but also being divided by 4. So if we thought of this according to inverse operations, this is being multiplied by 3, so let's divide by 3. Remember that fraction bar means divide. Let's take this 3 and divide that by 3. Now of course if we divide the left side by 3, we also have to divide the right side by 3. And then in this 3 over 4, that's divided by 4. The opposite of dividing by 4 is multiplying by 4. So let's put a 4 on the top. But if we multiply the left side by 4, we also have to multiply the right side by 4. And what happens here is beautiful, because now we know we already talked about multiplying fractions. The 3's divide, the 4's divide, and all we're left with is that y. So we have y equals, you might want to write this as 9 over 1. Remember, it is a lot of times nice to simplify before we multiply, so 3 goes into 3 once and it goes into 9 3 times. So this is 3 times 4, which is 12. Okay, if we wanted to check that one, 3 over 4 times y equals 9. Y is 12 though, so this is 3 over 4 times 12. Let's write it as 12 over 1. And let's simplify here. 4 goes into 12 3 times. 3 times 3 is 9. We get 9 equals 9. Checks out. Answer is y equals 12. Now why do we need to check? Is it absolutely necessary to check? Am I going to make you show your check work on tests? No, I'm not going to make you show your checks on tests. But it's a way to check to make sure you don't make a silly mistake, because I know none of us are perfect. I make silly mistakes sometimes. And this is something you can do on every test. You can always check your work to make sure you did your math right, because we do make mistakes sometimes. And you don't even necessarily need to write out the check. A lot of times you can do the checks in your head, especially for simple equations like this. Now we're going to go ahead and move on to some more complicated equations. We're still talking about linear equations in this section, but now we're going to talk about equations that require more than one step. And so I have a solving strategy here that hopefully you will get used to as the semester goes on. We're going to talk about it a lot over and over again. I like to talk about 4 steps here. The first step, I'd like to say, just do what you can do. That means do any kind of simplifying you can. That could be that you need to get rid of parentheses by distributing. It could mean that you need to eliminate fractions. We're going to talk more about how to do that here in a little bit. But basically you have to multiply everything by the least common denominator. We remember we talked about that a few classes ago. And then we could also combine any like terms. So this is really, if I were to kind of summarize that first step, what we're really doing here is simplifying what we can. Simplify if possible. Now, we sometimes will skip that first step. There's nothing to simplify. But a lot of times there is stuff that we can simplify. Distribute, get rid of fractions, combine like terms. Once you've done that, then we want to start to organize our terms. We want to get the terms with variables on one side and the terms with numbers only on the other side. So if our linear equation has x's, we want to get all the x terms on one side and anything that doesn't have x's all on the other side. And that's step 2. The third step is now we're going to isolate the variable. Remember this equation C from the last, or example C from the last section. This essentially is what we would have after the first 2 steps. We would have all the x's on one side and all the numbers on the other side. Once we've done that, notice we had to still isolate the x. We had to divide. And I have a little thing to help us remember this. I didn't give you this the last section, but if we take a real world example, we talk about marriage. Well, marriage and multiply both start with the letters M. Now, and remember inverse operations. How do you undo a marriage? Well, by divorce. Just so happens that divorce starts with the same letter as divide. So you undo a marriage by divorce, and you undo multiply by divide. So I say multiply, marry, divide, divorce. Multiply, marry, divide, divorce. And then the last thing, of course, we can check solutions. So let's try this process with an example. So do what we can do in the first step. Is there anything here that we can simplify? Are there any parentheses? No. Are there any fractions? No. Are there any like terms on either side of the equation? Not really. We have an x term and a number term. X term, number term. So we can't do anything there, but what we can do is move on to step 2 and start to organize here. Get the x's on one side, the numbers on the other. And I typically like to move, notice we have x's on both sides. I like to move the smallest x. Let's make a note of that. Let's move the x with the smallest coefficient. Remember, coefficient is the number in front. Smallest number in front of x. So that means I want to move the 4x because obviously 4 is smaller than 5. So how would I do that? I would subtract 4x because this is a positive 4x. The sign wasn't written in front of the 4, which means we just assume it's positive. The opposite of positive 4x is negative 4x. If I subtract 4x on that side, I also need to subtract it on this side. So the x's are going to the left. The numbers then need to go to the right. If I have all my x's on the left, then my numbers need to go over here, which means this negative 4 has to go. It's a negative 4. The opposite of negative 4 is positive 4. Now let's go ahead and cancel what cancels here. negative 4 and positive 4 are opposites. Those cancel. And positive 4x and negative 4x, those are opposites. Those cancel. So what we have left here is we have 5x minus 4x, which is 1x. And on the right-hand side, we have 6 plus 4, which is 10. Now, this is again another case. Do I really need the 1 in front? No, not really. If you feel comfortable with that, you can leave it there, but it's not necessary. And so we have our answer. Now, I personally think it starts to get kind of ugly and messy if we are writing things out the way we did in this example and the way we've done in all our previous ones, where we minus 4 and add 4, or minus 4x and plus 4 and plus 4. It's just a lot of stuff going on. I like to write it in a simpler way. So, and this is kind of the phrase I like to remember. I call it change sides, change signs. Has a little bit of a ring to it. Change sides, change signs. And when I mean change sides, I mean this means moving terms to other side. So, I mean, in this equation there's 4 terms. 5x, negative 4, 4x, 6. Those are all terms. If I want to move terms to the other side, if I want to change sides, I have to change the sign. In other words, if I want all the x's on this side, I want to move this positive 4x over to this side. It becomes a negative 4x. If I want to move this negative 4 to the other side, it becomes a positive 4. Now I could still write the positive 4 over here like we did, but we know those are going to cancel. And I could still write the negative 4x underneath this positive 4x, but we know that's going to cancel. So why do we really need to write it? Let's just move it to the other side and change its sign. The answer still comes out the same. There's nothing different. 5x minus 4x is 1x. And on the other side, 6 plus 4 is 10. I think if you can get comfortable with doing that, even though it may not be what you've learned in the past, it's going to make your equation solving process a whole lot more efficient. So I'm going to start to show you it that way from now on. I am not going to be writing the same thing on both sides. Even though we know that's what we're doing, we're going to be a little bit more efficient and not write it all out anymore. So let's move on to example B. Again, we could check the solution here. I'm not going to do that anymore because I want to move on with the video and not make this video go on too long. But we should know now how to check solutions. Let's go ahead and move example B. It says 2 parentheses x minus 3 plus 3 equals 9. Do what we can do first. Is there any simplifying? Well, yeah, we need to distribute, right? So this is something we know how to do. So if we distribute, this becomes 2x minus 3 plus 3 equals 9. Okay? And then now that we've gotten rid of the parentheses, we still don't have fractions, but there are some like terms now. We have a minus 3 and a negative 3, which it's nice. That turns out to cancel. And so this gets a whole lot simpler. It becomes 2x equals 9. 2x equals 9. Now, if we move on to step 2, it says get all the terms with variables on one side and numbers only on the other side. We have done that already. We have x's on the left and numbers on the right, so we're good there. we can now do step 3 where it says isolate the variable. And remember, this is where we say multiply, marry, divide, divorce. This x is married to the 2 by multiplication. How do we undo that marriage? We divorce it. Or in other words, we divide. So here, the opposite of multiply by 2 is divide by 2, but if we do it on the left side, we got to do it on the right side. So this becomes just x equals 9 over 2, which is an improper fraction, and I know some of us don't like to write it that way, but I'm alright if you just leave your answers as improper fractions. So there's our answer. And it's okay to have an answer that's a fraction. I know that's a little scary sometimes too, but we can do that as well. Okay, moving on to another example. This is getting a little more complicated, but if we keep the same principles, it's really not all that bad. Do what we can do first. Can we distribute? Absolutely. There's 2 places to distribute in this problem. So when we distribute, we get 7x minus 21 plus 5 equals 4 times 3x is 12x. We have minus 8 because we have a 4 times a negative 2 is a negative 8. And we have still that, don't forget to bring that minus 8 on the end here. That's still got to be there. So we distribute. There are no fractions, but there are some like terms we can go ahead and combine. Negative 21 plus 5 is negative 16. So we have 7x. Combining these two, we get negative 16. And then on the right side, the 12x stays, but the minus 8 and minus 8, that becomes minus 16. And we add those. Okay, now moving on, we have, now we're to step 2 where we want to see if we can get all the x's on one side and numbers on the other. And remember, we want to move the term that has the smallest coefficient for the x. You don't have to do it that way, but I like to do it. So this would be, with the x's, this is 7x and 12x. We want to move the 7x. It is a positive 7x, so when I change sides, we change it to a negative 7x, which means that's not going to be there anymore. We're moving that to the other side, which means the numbers are now going to go on the other side. So we want to move this negative 16 to the right side. The opposite of that is a positive 16, which is going to make that go away. So now when I combine those terms, it's negative 16 and positive 16, that becomes 0, which may scare some of us, but it's actually a good thing. It makes our problem more simple. And then on the right side, 12 minus 7x is 5x. Moving on to step 3, this x is married to the 5 by multiplication. How do we undo that? We divide by 5. If I do it on the left side, I got to do it on the right side. And this is the thing that trips everybody up. How can I divide x divided by 0? There's something about division and 0. Well, that's the other way. I can't take 5 divided by 0. We can't do that, but you can do 0 divided by 5. It's just 0. So that's our answer here. Our answer is x equals 0, which is perfect. Okay. Now the next example, since this video is running a little bit late and this is one of the more complicated ones, we're actually going to do this in class next time. So you can go ahead and leave that blank. We're going to cover that in class. And then we're also going to cover these contradictions, these other ones in class too. I don't want to have this video be too long. We're going to save the last few examples for in class. That'll give us something to talk about together. So let's go ahead and end this video up right here and make sure you do your My Math Lab homework. We'll see you in class.